Welcome to section 6.2, where we're going to start working on integrating exponentials and trig. And classic to me when I'm taking a look at all of these integrals, first of all, I want to review derivatives because I always like to lead you up to understanding why you have to memorize these things, right? So I'm in here and I'm seeing that there's a section that I put in on logarithmic derivatives and the integrals of logarithms. And then, it turns out it's not here at all. So I'm making a freestyle for this, and I'm double checking the book, and the freestyle will be for section 6.5. So for now, I see them on the screen, but we're not actually going to cover them, okay? I'll have another video for you on that. What we are going to go over is exponential derivatives and trig derivatives. So here we are. I'm skipping those top ones. You'll see them reappear later. If you take the derivative of an e function, like the derivative of e to the x is e to the x, but what if there's actually a function in here? And I'm saying that for each one of these examples, I am making sure that there is a chain rule piece that we need to make sure when we take the derivative that we remember to use the chain rule. And I put a purple pen up here so that I'm planning on using that purple pen in order to get this work done. And so then I'm going to talk to you about each one of those antiderivatives. So the first one then, what is the derivative of e to the negative 9x? It will be e to the negative 9x, but we want to do that chain rule piece, and that chain rule piece will be the derivative of negative 9x, which is a negative 9. So when I'm all done, I'll say that I have negative 9e to the negative 9x. And of course, if we were looking for a multiple choice answer, we would see it like this: negative 9 with e to the positive 9x. And that's important. Noticing that you see this is the final answer. It's important because one day I'm going to ask you to integrate that. And you're going to have to know, oh, hey, that's really just a chain rule piece that's on top, and I could use the negative exponent rule and move that back up into the numerator and find that integral. So then now I'll introduce to you that the integral of e to the u du is still just e to the u. It's just you should see that chain rule piece as some sort of constant that's in front, that's around, and we're going to learn how to figure out what that constant is and put it back into the correct place. For now, on this actual section of the homework, there's no chain rule piece, but I'm reminding you of what the derivatives are so that you can learn them, okay? So now I say then, if I want to take the derivative of 8 to the power of 7 minus x, well, what's the derivative of something to a power? Well, I'm going to get the natural log of that something, so natural log of 8, and that's in the derivative. That's not the chain rule piece. That's just supposed to be some sort of constant that's there for you. And then the derivative continues, and it says, write down what that original piece was. That's 8 to the power of 7 minus x. And then don't forget that chain rule piece. All right, so the chain rule piece is the derivative of 7 minus x. So d dx of 7 minus x is going to be 0, and the hidden invisible constant there is a negative 1. So my answer will be 0 minus 1, which is just a negative 1. And so in the front, you'll see a negative natural log of 8, and you will see that being multiplied by your original piece, which was 8 to the power of 7 minus x. And there you go. So now when you look at the integral of a to the u, notice that you are going to be surprised. Why is there a natural log of a in the denominator? Well, here's the thing. So if I most of the time, if I gave you an integral of this, you would be able to pop an answer out immediately. You'd be like, boom, boom. I can see that natural log of 8 in front. I can see that 8. In fact, I can even see that little chain rule piece because the derivative of this is just a negative 1. So that actually makes the problem too easy. So what I'm going to do is I'm going to give you the integral, ready, of just 8 to the 7 minus the power of x. And you are going to have to figure out, where did the natural log go? I wanted there to be a natural log in front, and there isn't a natural log in front. So I'm going to teach you a process where you're going to end up creating that constant that was missing. And we practiced this a little bit in the last section. So if I had given you the integral of x to the fourth, you recreated that integral like this. Have a 4, have a 1/4 out in front, have an integral, and then have an x to the fourth, and times, the thing we wanted to create here was actually, hold on, sorry about that, a 5, because remember, we know what the integral of 5x to the fourth is. And so all we had to do was put a 1 over 5 in front. So I'm trying to teach you, when I ask you to memorize this guy, I'm trying to teach you that you don't see the constant. That's okay. It's just something that's, a divisor once you're done integrating. Just like this is a divisor that still stays there when I'm done integrating. So I'll have that 1/5, and then I'm sorry, I keep doing it. Apologize for that. That 1/5 and an x to the 5th power. Okay, so that's why I'm asking you to memorize it that way, so that I can give you harder test questions than that, where you can already see that the natural log exists and it's in the right place. I'm trying to make a problem where there's actually work for you to do. Now, moving on then, how about these other integrals? So I'm saying that I have the derivative of sine of 10 of x, sine of 10 times x. And so what's the derivative of sine? What is the derivative of sine? It's cosine. So I'll have cosine, and there's that interior function, which is my 10x. And then remember that chain rule piece says that you should multiply by the derivative of 10x, which is just a 10. So that's the derivative. So what's the antiderivative? Oh yeah, by the way, I agree. I'll have a 10, I'm going to have a cosine, and I'm going to have a 10x. And what's the antiderivative then of sine? Well, look at this. Wait a minute, what? Well, I said, what's the antiderivative of sine? But the fact of the matter is, if I ask you to find the antiderivative of this, what are you actually finding the antiderivative of? You are finding the antiderivative of cosine. So this guy matches with that guy. Do you see? The antiderivative of cosine, if I want to integrate this, I should get sine. Okay, let's try this one more time. So say that I took the derivative of cosine, and there's an x squared. I'm going to get that negative sine, because, right, the derivative of cosine is negative sine. I'm going to get negative sine, and that's an x squared. And don't forget your chain rule piece. Your chain rule piece says take the derivative of the inside. I'm going to get this 2x, right? So then when I want to integrate this, what am I integrating? I am integrating, dun, 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 I am integrating sine. And notice that my version of sine, I do not want you to memorize the integral of negative sine. No. I'm asking you to memorize the integral of just a plain old sine. Again, if I put the negative out in front for you when I'm asking you to do an integral, there's not much work for you. You already know that the derivative of cosine is negative sine. See? So these guys match in the following way, and that's why we ask you to memorize the negative for cosine, that, like that. So we're just trying to make it so that we actually have a question to ask you, like, well, where did that negative sign go? When do you need that negative sign? And how do you go forwards and how do you go backwards? Okay, so then the next one, I want to take the derivative of tangent. And when I take the derivative of tangent, I'm supposed to get a secant squared, okay? So I'm going to get a secant squared, and there's the 9x, Whoops, there's the 9x. And don't forget to do that chain rule piece. That chain rule piece is the derivative of 9x, which is a 9. So when I'm done, I take that 9 and I put it out in front, and I have a secant squared, and there's my 9x. And by the way, I'm realizing I never finished this one. This one would be a -2 times x with a sign of x squared behind it. And so what I'm saying to you right now is during this homework, there is no chain rule, but I wanted to kind of introduce to you that when you see a thingy in front, it comes from the chain rule. When you see a thingy in the front, it comes from the chain rule. When you see a thingy in the front, it comes from the chain rule. And here was your thingy in the front, and here is the thingy in the front, and those are all our chain rule pieces. So when you're doing these integrals, I think they're going to turn out to be like way simple in your mind. It's going to happen really fast. I'm just trying to like load up for using the chain rule. So now what's the derivative of secant? It's going to be secant u tangent u. So I'm going to get a secant, and that's going to be an x to the fourth because that's my u. I'm going to have a tangent, and that's going to be x to the fourth, and that's my u. And don't forget my chain rule piece, which is the derivative of x to the fourth, which is going to be 4x cubed. And that chain rule piece should come out in the front if I'm writing my final answer. But I'm moving on now because I've already spent a lot of time on these, okay? The last two of them, cosecant. If I take the derivative of cosecant, I get negative cosecant u, which is in this case a -5x, and cotangent u, which again will be of -5x. And then don't forget that chain rule piece. The chain rule piece is supposed to be ready. It's supposed to be ready. It's supposed to be the derivative of -5x, which is a -5. And that would go in front. And this one I'm actually going to finish because this combines with this, and what we end up with is a +5 in front. So then the rest of it will be the cosecant of 5x and the cotangent of 5x. And wait a minute now here. Hold on a second. Again, I have this weird thing where if I'm asking you to find the antiderivative, and I'm going back to these two as well, because I didn't really talk about their antiderivatives. Look at this. The antiderivative of secant u should be tangent u. So if I show you an integral of this guy, you're supposed to immediately know, hey, I took the derivative of what? I took the derivative of tangent. Now, if I give you an integral of this next piece right here, and I say, hey, the antiderivative, find it for me, you've got to be able to say, oh, well, I see a secant and a tangent, so you must have done what? You must have taken the derivative of secant. And then this last one right here, if you see a cosecant and a cotangent, a cosecant and a cotangent, and by the way, here's your little chain rule piece, then you know that the antiderivative of cosecant and cotangent should be cosecant, just like it says right here. Cosecant. Whoops. These are out of order. Sorry about that. That goes with that one. I'll fix that on the make it cheat sheet. I apologize. So yeah. And by the way, notice that what I'm doing here is, again, I'm asking you to memorize the positive is over here, which means that in your answer, you will get a negative, because on a test, if I give you this, there's not much work for you to do. You've already seen the cosecant, the cotangent. You can already see the -5 and the x. You could see the chain rule piece. You could see that I took the derivative with a negative in front. No, I want to give you this, and you have to undo the negative times a negative business that we had, and you need to recognize that this 5 comes from that chain rule piece. And in fact, on a test, I'm going to be more mean than that. I'm going to put a constant like a 10. Or I'm going to be even meaner than that. I'm going to put a constant like an 8. And you're going to be like, well, where did that 8 come from? And that's the constant that you're going to have to find. And so we're getting into that in the next couple of sections, all right? All right, one more try here. What's the derivative of cotangent? The derivative of cotangent, whoops, again, I'm sorry, these are out of order. Look at this. If I take the derivative of cosecant, it goes like that. So I'm going to fix the mega cheat sheet right as soon as I'm done making this video. So let's see, I'm here and I'm saying that the derivative of cotangent is cosecant squared, and the inside function is my negative 3x. And by the way, the derivative of cosecant is a negative, so there should be a negative out in front. But guess what? I already had a negative in front, so now it becomes a positive. And then don't forget your chain rule piece. The chain rule piece is the derivative of negative 3x, which is a negative 3. And so when I end up putting all of that together, I get a negative 3, and here's your cosecant squared, and there is your negative 3x. And now, boy, this looks great, doesn't it? You can really tell that what the integral is. The integral of cosecant squared u, wait a minute, should be a negative. Oh, well, here is my negative. This is a moment where I really need you to pay attention to signages. So the derivatives of cotangent and cosecant and of cosine all generate a negative. And so when I want you to memorize these integrals, I want you to pay attention to which integrals will also generate a negative. All right, so that is the introduction to this section. So now I do want to remind you again about sign errors. I just mentioned it, but let me mention it again. And I really feel like this chart would be better if there was a little arrow right here and a little arrow right there. All right, let's talk about it. In the simple diagram at the right, reminiscent of the unit circle, it could help you in remembering the rules for these two functions, which are used far more than any other trig functions. Rotate clockwise for derivatives, rotate counterclockwise for antiderivatives. And here's what he's saying. If I want to take the derivative of sine and get cosine, we're talking about we're talking about that arrow right there. And so the derivative of sine is cosine. Now, if I want to take the derivative of cosine, what should I get? I should get negative sine. And that would be this arrow right there. And then if I want to go backwards, I want to find, ready, the integral of cosine should be sine. Because remember that this purple arrow, if I want to go backwards, I would get the red arrow, okay? And notice that is right here. The integral of cosine is just plain old sine. And here I'm going to try and stick to the colors. I feel bad. I pulled out that red on you. Here I'm going to stick to the green. If I was taking the derivative of cosine and I got negative sine, well, then when I want to take the integral of sine, I should get, ready, negative cosine. And so that's that arrow right there. And this is this integral right here. Now, this is just a trick that he, kind of lays out for you. And I don't know if you like it or not. I know you guys are really good at memorizing things. So I say just memorize that and just memorize that. And then we move forward and we're very happy. Okay. And I'll show you how to use it just like you've memorized it as well. All right, so when I'm looking at this integral for number 1, I see that there's a negative 3 out in front. I don't have that memorized. I don't have the integral of negative sine memorized. What I have memorized is the integral of sine is negative cosine. So what I do is I will take that negative 3, I'll put it out in front. It's very distracting to me. I just want to find the integral of sine of x dx, and I will say the integral of sine x dx is negative 3 cosine x plus c. Ta-da! See? It works out really easily to do it like that. All right, so then for number 2, oh, wait, I apologize. I thought I had saved myself a spot. Okay, I'm just going to try and write really, really small here. All right, so what's the integral of e to the x? It should just be e to the x, right? That part's way too easy. There's no negatives. There's nothing to deal with. I'm not worried about it at all. But that negative 2 to the power of x, again, remember the beginning part of this video, I said, hey, there's supposed to be some sort of natural log here, right? No, I'm going to ask you to memorize this particular integral. There's no natural log of a involved at all. So therefore, when I was taking the derivative, something must have canceled out. And so I can just go backwards like this. Ready? There's a minus sign, and here is my 2 to the power of x, and it should be, the integral should be that negative 2 to the power of x and a natural log of 2 goes in the denominator, and there's a plus c. Ta-da! Okay. And then, and be careful with notation here. Remember, I have these leading equal signs. You do not put some sort of weird integral symbol there. Okay, you have taken the integral, and therefore your answer is that. And so if you're feeling compulsive and you have to put something in front of your equal sign, the thing to put in front of the equal sign is the entire business that you were asked. So that's why I'm really trying to train you to save time and not write down any of this. Just write down that leading equal sign, okay? So over here, I'm narrowing in, and I'm saying I don't even recognize this, right? What are we doing? That's not on here. Well, I mean, you know why I like this book. It's, you know, he reminds you of what we did in the last section. The last section was the reverse power rule. So this must be some sort of hidden power. Ready? It's the integral. I'm going to throw that 5 out there because it's very distracting. I don't need it right now. This is t to the 2/3 power. And there's also another integral, and here's the integral, 3 with the integral of cosine of t. And then there's one more integral, and the integral is negative integral of 1 and a dt. Very nice. Now, double check on the mega cheat sheet. Am I allowed to do this? Is this a thing? Yes, I am. And I put it on the mega cheat sheet specifically so that you recognize it. If you have some piece, plus or minus some other piece, you can separate these integrals into 2 different pieces. Now, there is a little bit more to my mega cheat sheet. I am reminding you what to do if there's something called limits of integration. And those limits of integration are numbers that help us figure out what the plus c part is. Because when you're memorizing these integrals, there's a plus c, right? Well, these are all called indefinite integrals. And I used to, right here on the mega cheat sheet, I used to have the words indefinite integrals. But I ended up adding some more things and there just wasn't room. So I'm going to put it back in there. It's supposed to say that right here, that those are indefinite integrals. And so you remember, hey, there's no limits of integration. We're going to work on limits of integration. I don't know. It's like 2 sections from now. So we're coming back down here and we're saying, are we allowed to sort of split this up into all these separate integrals? The answer is yes. But I did forget to write dt right here, and I did forget to write a dt right here, and the graders don't care if I forget that. That's not a problem for them. They know how often that happens. There's supposed to be a leading equal sign, and boom, now I'm going to use the reverse power rule. I have that 5 out in front, and you know what would have been handy actually is for me to say, hey, I'm bringing up my power from 2/3. I'm going to add 1 to it, so that's 1 and 2/3, and I want to write that as a fraction, so that's actually going to be, ready, 3 and 3/3 plus 2/3, which is 5/3. Aha! Now I know where that 5 comes from. Whatever. I'm not worried about it. I'm going to write this integral like this. Ready? I'm going to write it like this. This is, sorry. You know, I don't even want to do that because that's just not my method. You guys are the ones who are really good about putting that piece in there. Me, I'm going to do it my way. I'm going to say that I have t to the 5/3 and it is divided by 5/3. Now, on the AP exam, you can leave it like that. I know it looks ugly, but unless you were doing a multiple choice problem, you'll see that be worked out. 5 divided by 5/3 ends up being 5 times 3/5, which means that there was really just a 3 out in front. So I'm going to write my answer, ready, as 3t to the 5/3. Now, What's the integral of cosine of t dt? It is, what's the integral of cosine? What's the integral of cosine? Ta-da! It's just sine. You were wondering, is there a negative sign? You know what I do in order to double check? I make sure that I just do the derivative real quick. What's the derivative of sine? It's cosine. Those both things are both positive. So if I'm going from cosine back to sine, I want to make sure that I am keeping it positive. Now, if you wanted to use this, remember we're doing this. Cosine goes to sine, and sine should be positive. So here we go. I'm saying that this is a 3, and it is a sine of t, and it is positive. Now, what's the integral of 1? It's negative 1x, and there should be a plus c. All right. Number 4, we've got the integral of secant y tangent y. Think about it for a minute. If I take the derivative of something and I got secant and tangent, what did I take the derivative of? Yep, that's right. I totally took the integral of secant. I took the derivative of secant. The derivative of secant, sorry, it's over here. The derivative of secant is secant tangent. So if you see a secant tangent, you're going backwards. The backwards piece would be, ta-da, secant. All right, so now that means what? Well, this is really 1/4 times the integral of secant y tangent y, and there's my dy. And so I'm going to get 1/4 and secant y with a plus c. The last example is a little bit more complex, and I want to say, looking at it right now, I can tell that something's off, right? Something's off about number 5. Do you recognize it? Didn't I want cosecant to be squared with the 2 right? Where is it? I wanted that cosecant, that 2 to be right there. Yep, that's the piece that's off. So yeah, you can rewrite this. If this guy is equal to cosecant squared of x, yes, now I can find the integral of it. And what does that look like, by the way? And I'm not going to cheese it. I'm actually going to write it really nicely, okay? The integral of a derivative is just that original function. Integral of f prime of x dx is f of x, okay? And therefore, what is the integral of, I meant all that to be in a different color. Okay, cosecant squared x dx. Oops, sorry, this is the piece where I'm adding it, right? It doesn't look as good as here's what I do in the classroom. Ready? Integral here, dx. Integral here, dx. You see what I'm saying? I was just trying to make it look nice down here. I'm saying you are applying an integral to both sides. And the way that I do this in class prior to this moment would have been with taking the square root of both sides or squaring both sides of an equation. You're allowed to take an integral the same way you're allowed to take a square root, or to take something and square it to get rid of a square root. Let me remind you what those look like. So if I have the square root of x equals 3, I taught you, ready? You're allowed to square both sides. You're allowed to square both sides, and that's how you know that the answer is positive and negative. Yep, positive. No, is it positive and negative? No, I think it's just 9. Okay, but let me think about the squaring of something. So I have square of something, and I want to go backwards on that. I taught you that you can, ready, take the square root of both sides, and therefore the answer here is positive or negative 5. The integral works the same way. If I say that f prime of x equals, I don't know, why not just do like 4x? Well, you can apply an integral here, and you can apply an integral here, just like we did for those other two, okay, in order to find the antiderivative. Okay, so now then I'm taking a look at this guy, and I'm saying, well, what is the integral of cosecant of x? So cosecant squared. Is it what you think it is? Let's double check. It is negative cotangent of x. And that's why I have you memorize the negative that's why I have you memorize it with the answer is negative. All right, so here my answer will be negative cosecant Did I just say cotangent? I just said cotangent. Cotangent of x. And it's plus a c, right? It's plus a c. Well, wait a minute. How come we have to go further? Because he gave me the initial conditions. These are my initial conditions. Okay? My initial conditions tell me that I know what it is when I evaluate it. When x equals this, y will equal that. So here we go. I'm about to use this. If x is supposed to be 5 pi over 4, and here's my negative cotangent, and then y equals 3, I will be able to find out what c is by solving for that. Now I'm going to go back to my unit circle and I'm going to think about this 5 pi over 4 business. And so let me do that. When I'm looking at the unit circle, remember that this is pi over 2. Therefore, a pi over 4 is here, and there's another pi over 4 here, and there's another pi over 4 here, and there's another pi over 4 here. 5 pi over 4s is a whole pi plus one more of them, so that lands me right here. And the thing I love about pi's over 4 is that this point right here, this point is going to be the square root of 2 over 2 and the square root of 2 over 2. And when I put those two things on top of each other, because remember, cotangent is going to be what? It's going to be, cotangent is defined as being cosine of something over sine of something. And let me go back to the Make It cheat sheet and show you that real quick. It's right here. Cotangent is, well, there's my reciprocal identity. I'm not using that right now because it's not very helpful to me. Cosine of something over sine of something. Okay, so then I'm going back here and I'm talking about my unit circle. If I put this on top of this, right, because that's what I will get is I will get the square root of 2 over 2 divided by the square root of 2 over 2. Well, guess what? That's just 1, because something on top and the same exact thing on the bottom, that's just 1. It's kind of fun to play around and actually do that division because stuff cancels out, but eventually you end up with 1. So what I love about stuff with pi's over 4 is that I know if I'm doing cotangent or tangent, I will get a version of 1. Well, here the answer will be 1. Here the answer will be negative 1. Why? Because I'm on the negative part of the x-axis. And so then what will this be? This one will be a positive 1 again. Why? Because I have a negative over a negative, because x is negative and y is negative here. And this, I will also get a negative 1. Why? Because instead of x being negative, y will be negative. So these are actually really nice and very easy to work out. And let me do this one more time in one other way. He says on his answer key, he says, look, what if we had a reference triangle right here? Our reference triangle is, what is this location? This location is, ready? Negative square root of 2 over 2 and negative square root of 2 over 2. But what are my distances? My distance is that this is 1 and that distance is 1, and therefore I should have a square root of 2 as my length of the hypotenuse, which is how we ended up getting that. This number was negative and that number was negative. Therefore, cotangent of 5 pi over 4 can easily be memorized as being, ready, equal to 1. And that means that I have 3 equals negative times 1 plus c. And let me solve that. I am going to add 1 to both sides, and I end up finding out that c equals 4, and therefore f of x is really, ready, negative cotangent of x plus 4. Ta-da! Good luck on the homeworks. I'm noticing that these are all quite simple, that do not have any initial conditions. And let me know if you need help on those. The ones with initial conditions are the ones you really want to make sure you ask me about in class.